Recording in progress.
All right, good afternoon. We are moving on to Unit 3. It's a whirlwind during the summer, isn't it? All right, so we are moving on to numerical methods. Hopefully you've watched the video talking about this because we're going to kind of speed through it, but we'll go over it a little bit. So numerical methods. Actually, I want that to be a little bit fatter. So numerical methods. Actually, there we go. All right, so numerical methods. Here we go. All right, so step 1, generate a grid. So you have some medium through which you have heat transfer. All right, so create a grid. So I'm going to draw some boxes. I know it's not terribly pretty, but just bear with me, okay? Pretend like it's a very pretty grid, okay? It's not great. That's all right. All right, so I'm going to draw a dot in the middle of them. So each one of those boxes is what we call an element, and each of the dots is what we call a node. And the node, the temperature at that node represents the average temperature of that element. And we're going to name each one of those nodes, actually. Name those. So the node of interest is going to be, stop it, M, N. So it's like X, Y coordinates, right? And then we'll have that. We'll have M, N plus 1. Then we'll have M, N minus 1. You see how we're going here? And then this will be M plus 1 N. This will be M minus 1 N. All right. And so our node of interest is going to be right there in the middle, that dot there at the very, very middle. And all right, so we've generated our grid. We do need to put some dimensions here. So the dimensions of each of these elements, so this would be delta y, and that means that the temperature, the distance between each of those nodes in the vertical direction is going to be delta y as well. And then this guy would be delta x, right? And then the distance between the nodes in the x direction horizontally is going to also be delta x. Perfect. And yeah, we'll talk about what happens if delta x and delta y are equal to one another, but they don't necessarily have to be. If they're equal to one another, our equation gets a little simpler. But again, they do not have to be equal to one another. So yeah, so this is our grid generation. Perfect. And while we could use this for 3 dimensions, we are just going to be focusing on 2-dimensional steady state heat conduction or heat transfer. So 2D only, meaning that, okay, you have heat transfer and a temperature gradient in the x direction, in the y direction. And then if you want to consider things into the paper, that's delta z, or into the screen, that's delta z. But your delta z is just 1. It's just 1. So sometimes we'll write it, sometimes we won't, and you'll see where that comes into play. All right, step number 2 is apply your energy balance. Right? And just a very generic energy balance. So E dot in minus E dot out plus E dot G equals E dot stored. So let's do that. And I'll actually make this a little bit. There we go. So I have E dot in minus E dot out. Perfect. Plus, I'll have a E dot stored. Not E dot stored. E dot G. And then I'll have, oops, a little bit. And I'll have an E dot ST. All right, so the rate of energy stored, that guy is going to go away if it's steady state. So, and for all of these numerical methods problems, they're all going to be steady state. Your book does go into how we would treat things, how we'd use numerical methods if we had non-steady state, but we're not going to do that just because we don't have enough time. So, but again, 0 if it's steady state. We won't necessarily, let's leave the E dot G alone. Maybe we have energy generation, maybe we don't, we'll see. Now, as far as the E dot in and E dot out go, so you're looking at that central node MN. And the way that we're going to look at it is, okay, I've got these 4 neighboring nodes. This is an internal node. And I've got energy being transferred by conduction between each of those nodes. And the way I'm going to do it is I'm going to draw all of those Qs coming into the node. Now, I know that's not really what's going to be happening, but I'm going to do that just by convention, and then the math is going to tell me whether, what direction the arrows are actually going. So if we calculate one of those Q's as a negative number, well, it just means it's flipped around, right? All right, so you'll notice, I don't have no arrows going out, so this goes away. All right, so let's go ahead and we're going to start at 10 o'clock, or not 10 o'clock, at 12 o'clock, right there at the top. I'll make this a little bit darker, that green. So the way it's going to be, so it's Fourier's law, because again, this is by conduction. So we have negative K, and it's negative K times the area times dt dx. That's how we would write Fourier's law, right? In fact, I think I want to write that. Just, so negative K A dt dx. That's Fourier's law. That's Q, right? In the x direction. We've got in the y direction as well, so you'll see different, but that's what we think of when we think of Fourier's law. All right, so I've got the negative K, and then I need the area. So the area through which this guy goes is, well, it's going to be this area right here. So the area cross-sectional, the area that's perpendicular to that vector going down is going to be delta x times into the screen times this guy right here. So let's write that. So negative K times delta x times that 1. That's the area through which it's going. All right, and now I've got the dt dx part, which is not really a dt dx. All right, so the dt is going to be, so it's going to be T mn minus the temperature of that neighboring node. T m n plus 1. And then this dx, remember that just represents the distance between the distance between those two temperatures. And so what's that going to be? Well, it's delta y, right? Perfect. And then we're just going to keep on keeping on. So I have another negative k. So the one coming from 3 o'clock from node m plus 1, comma n. So at 3 o'clock. So this is going to be, well, the area is going to be this area right here. So it's going to be delta y times 1. And then we'll have this a little bit, we'll have a t m n minus t m plus 1 n over a distance of, well, that distance between those two nodes is going to be in the horizontal x direction, so it's going to be a delta x. All right, so we're going to keep on keeping on. So coming down the bottom one, so at 6 o'clock, coming in from 6 o'clock, we have negative k times this area right there. So it's going to be dt, or dt is going to be delta x, right, looking at our dimensions up there, delta x times the distance into the screen, which is delta z, but again, it's a two-dimensional problem, so it's just 1. All right. Now I have t m n minus t m n minus 1 over the distance between those two nodes, which is just delta y. All right. One more coming from 9 o'clock, coming from the right. So I have negative k, this area right there. So that area is going to be delta y times in the z direction, which is 1. And then I have t m n minus t m minus 1 n over the distance between those nodes, which is just delta x. So those are all the heat transfer vectors due to conduction from all the neighboring elements. But then I also have, I've got the E dot G portion. Now, what we would be given is a Q dot. So the units for all 4 of those conduction vectors, that's going to be in watts. This Q dot, remember, he's in terms of watts per meter cubed. So I need to multiply him by the volume of that element. So the volume of the element is going to be, well, it's delta x, delta y, delta x times delta y times delta z, which again is just 1. Perfect. All right, and then that's all equal to 0. Perfect. So it's kind of ugly, isn't it? And if our delta x and our delta y, if that node spacing is equal to one another, our math gets a little bit easier. And what it's going to boil down to is this. We'll have T, and it's the temperatures at all of those neighboring nodes. So T m n plus 1 plus, all right, at 3 o'clock, T m plus 1 n. And from 6 o'clock, T m n minus 1. From 9 o'clock, T m minus 1 n. Okay, and then it's going to be minus 4 times the node of interest, the temperature of the node of interest, which is mn, Tmn. And then we're going to have the Q dot term. So it's going to be Q dot times, and if that spacing is the same, again, it's going to be delta x squared divided by K. That's where that K went, in case you're wondering where it went. All right. So that's for an interior node with heat generation. And if you look in your book, I think it's either chapter 4 or chapter 5. I cannot remember off the top of my head, but there is a table of energy balances for various nodal arrangements. I would not suggest that you try to memorize those, but I would suggest that you see if you can derive those yourself. That would be a great way to kind of study this and make sure that you understand how to get the governing equations, because those governing equations, like the one that we just circled in a happy cloud there, those are going to be used for calculating what the temperature is in a big nodal network. Okay, now big nodal network, well, for our purposes we're going to be doing this by hand, so maybe you might be looking at like 3 unknown temperatures. Okay, so it won't be too bad, but you do need to be able to set up the problem. Okay.
So for the thing you just went over,
Yes.
you mentioned that we have access to those governing equations, but that we are going to need to be able to just solve for them for the exam. I just wanted to make sure I had that correct.
Well, it's not in your packet. It's not in the
Oh,
heat
okay.
transfer packet, but yeah, if you flip through your book, again, I can't remember if it's chapter 4 or 5, but there's a table of derived energy balances, and it would be a good like way to kind of practice deriving the equations on your own, make sure that you got it.
Okay, so just do all of those, right? All of the different derived ones. Just make sure we can.
It would be a good way to study. How's that?
Okay. All right,
Yeah.
sounds good.
Yeah. All right. So, let's do this one. All right, so we have, this is, I guess nodal configuration 2 is the second one in that table. But we want to find the finite difference equations under steady state conditions. Again, all of these are going to be steady state for the following situations. So this one's a little bit different from what's in that table, because for A, we're going to say instead of having convection all along here, we're insulating this, the horizontal surface here. So while we've got, if I'm going to draw my heat transfer vectors, okay, I've got these neighboring nodes, and so I'm going to draw some Q's going like that. And then I also have Q by conduction into, or I'm sorry, Q by convection coming into that element as well, but it's only coming in like at the half area. Okay, and then B, it says both of the boundaries are, both these boundaries are insulated. So let's just worry about case A right now. And case B will be really simple to follow, you'll see. All right, so assume. All right, so steady state, two-dimensional, that's about it, steady state. All right, so what we're going to do is we're going to do the same thing, energy balance on that node M in. So energy balance on node M in. And so we don't have, we've got so it's E dot in minus E dot out plus E dot G equals E dot ST. Everything's going to go away except those E dot ins. So basically just summing up all of those vectors, those 4 green vectors and the blue vector due to convection, all of that's got to be equal to 0. So let's start up at 12 o'clock, the one on the top. So Q coming from the very top. So I have, all right, so I've got negative K, the area through which that heat transfer is going perpendicularly is going to be delta X. Yeah, so it's going to be delta X times 1. I like putting the 1 there just so because it's an area, right? And then I've got my dt on the top. So this is going to be T m n minus T m n plus 1 over the distance between those nodes, which in this case is delta y. Okay, got one. Let's go to the one at 3 o'clock. So I have negative k, and that area is actually a half area. So it's not delta y, it's delta y over 2 because it's just this, right? As opposed to that whole area, it's just this. So it's going to be delta y over 2 times 1. There's our area. And then I've got a T m n minus T m n plus 1. And then the distance is still just delta x. Perfect.
Shouldn't it be T m plus 1 n?
Yes, it should. Good gracious. Go away, you. Good enough. Okay. M plus 1 n. Thank you very much. All right, and then coming up from 6 o'clock, actually, we'll do the convection as well. Let's do the convection. So Newton's law of cooling, well, it's going to be H times the area. Again, it's just a half area. So it's just this half area right there. So it's going to be delta y over 2 times into the screen, times the distance into the screen, which is just 1, times, all right, and it's going to be the temperature at the beginning of that arrow minus the one at the ending of that arrow. So T infinity minus that T m n. Okay. I don't know why I've all of a sudden changed to black there, but there you go. And then I've got I've got 2 more vectors, one at 6 o'clock and one at 9 o'clock, and then we'll be done with that. So the one coming in from 6 o'clock is just going to be negative k, and it's a half area again. So it is delta x over 2 times 1, and then this is T m n minus T m n minus 1. Over the distance, which is just delta y. And I got one more. The one coming in from the left, from 9 o'clock. So I have negative k. Area is a full area, so it is delta y times 1. And then I have Tmn minus Tm minus 1 in what is the black line an adiabatic surface? Yes, so that this guy right here that I drew, yeah, because it said in part A, it said the horizontal boundary of the internal corner is perfectly insulated. So I put, yeah, sorry. And then the distance between the node m minus 1 n and then the node of interest is just delta x. And there's no energy generation, like I said, and all of that's equal to 0. And that's kind of it. That's all I needed for A. And I could pretty it up, but there's really not a need to do that. So, yeah. So that's A. For part B, it says, well, what would it be? What would your balance be if both these were insulated? Well, if both of those surfaces were insulated, it'd be the exact same thing, just wouldn't have any convection. So same, but there would be no convection term. Easy peasy. So copy, paste, no convection. All right. All right.
Can you explain why we don't have, for the first term, why it's not over 2? So it's negative k delta x.
It's because it's going through this whole area right there.
Okay, so you just took the difference between the two.
The difference between the two. Well, that. So that distance right there is delta x, right? And so the area would be delta x times delta z into the screen. That would be the area through which it's going perpendicularly. Delta z is just 1.
Okay.
Yeah. All right. So the question was, in a nicer way of asking it, how long are we going to be here? What problem did this morning's class get to? We got to all of the we got through all of the finite element stuff. So we will start transient conduction tomorrow. So once we get to that point, we're done. Sound good? All right. Problem 2. All right, so we have a nodal configuration, and we are going to derive the finite difference equations under steady state conditions for the following situations. So, okay. I was kind of lazy before. I didn't actually write it. So we're going to find the finite differential equations if, and we have a couple of situations. What if? I like that one. Okay. If we'll say the top so it says for part A, it's the upper boundary of the external corner is perfectly insulated. So I'm gonna put like some insulation up here, and I'll try to color code it. So the top, and it's the whole thing, but the top surface is insulated. And then B, it says both boundaries of the external corner are perfectly insulated. So we would say the top and the vertical surface are insulated. All right. Only thing I really need to assume is that everything is occurring at steady state. Here we go. Perfect. All right, so we have no energy generation, I don't think. So it's just going to be the Q by conduction going into that node. Oh, and convection, right? So I am going to, if it's all right with you, I'm going to erase this green so I don't get confused right now, and then I'll bring him back when we start talking about B. But if it's just the top surface, all right, let's draw those vectors. So I have a Q by conduction coming from the left. I have a Q by conduction coming from the bottom. And then I also have a Q by conduction coming in right here. So let's sum them all up. All right, so I'll start at 3 o'clock. I'll start with the convection. So for A, so my finite difference equation is going to be H times the area. And what you'll notice is that, and actually, you know what? I'm going to change it. I am actually going to add, say, Q dot is not equal to 0. Say we have some sort of heat conduction, or heat generation, internal heat generation. Let's say that we have it. So what you'll notice is that this is a quarter of an element. So the area through that this blue arrow is going into is a half area. So it's going to be h times delta y over 2 times 1. And then we'll have our T infinity minus T mn. All right. Now we'll go to the Q by conduction coming up from the bottom. And that's going to be negative K. And that area, again, it's a half area. So it's going to be delta Y over, I'm sorry, not delta Y, delta X. Delta X over 2 times the 1 into the screen times Tmn minus Tmn minus 1. And then the distance between those is going to be delta y. All right, now we got to get the vector coming in from the left. So it's going to be plus, making it worse, plus negative k. And then that area, again, it's another half area. So it's going to be delta y over 2 times 1. And then we have Tmn minus Tm minus 1n. And then if we have internal heat generation, if we have a Q dot, we need to add him. So let's say we have a Q dot. Well, the volume of that element is really a quarter of an element because the whole element would be like this. It would be that size.
Did you forget to divide by delta x in the third term?
I did, yes. Yes, thank you. Thank you very much. All right, so that area or that volume is going to be delta x, delta y times 1, right? Because it's a volume, but divided by 4 because, again, it's just a quarter of an element. And then all of that's equal to 0. And that's really all we need, right? And then for B, if the top and the side is insulated such that you don't have any convection, well, again, it's the same, but there's no convection term. Easy peasy. All right. Okay, problem 3. All right, so we have a square channel, and I'm going to zoom into it if you don't mind, because I want to make sure that we've got it. So we have a square channel, and it looks like the interior of this channel, this whole surface on the middle, that's all this temperature right here. And what they've done is they've got a cutout. So they've taken this little section right here. That's this section right there. And what they've said is, okay, well, because we have, well, we've got convection all the way around, right? Convection out here, all the way around. We've got symmetric thermal symmetry for this thing. So if I figure out the temperature distribution in this, I figured it out for the rest of it because it's just kind of copy paste all the way around. You see what I'm saying? So yeah. Because this is a line of symmetry. So if you kind of like think about it as a mirror image. So like this right here, and this right here, if you flipped it over, it would be a mirror image as far as the temperature distribution goes. So the question is, how do you determine how many nodes per section? Depends on how accurate you need to be, right? So the tighter your mesh, the smaller those delta X, delta Y's are, well, you're going to get a much more accurate depiction of that temperature distribution through your medium, but it's going to be more computation time. So it's a trade-off. All right, so let's look at that little chunk that they gave us. And I'm going to try to color coordinate it. So at the bottom, that's where that whole surface there is at 600 degrees Celsius, 600 Kelvin. So that bottom line, that whole bottom line, and the nodes on that line are 600 Kelvin. And then of course I've got some convection going on out here, and that's exposed to nodes 1, 2, 3, and 4. And then they do give us some temperatures here, and I think I want to try my best to sort of color coordinate them, okay? So T1, I'm going to kind of highlight him because I just want it to be really obvious when I look at that I know what that is. And then T3, that's this guy, so I know him. I know, let's get some different. Yeah, pink is good. 8. Oh. 8 and 9. Oh, that should have been red. 8 and 9 are at 600. And then 6, that's going to be this guy right here. Okay, so I've sort of made the nodes that I know what the temperature is, made those colored. So it's kind of obvious. Okay. And I want to know some stuff. I want to get, it says defined, beginning with properly defined control volumes, derive the finite temperature equations for nodes 2, 4, and 7. So I'm going to have 3 equations by doing an energy balance on nodes 2, 4, and 7. And then we need to find the heat loss per unit length from the channel. Okay. All right. Okay, so that's fine. All right, so I think before we start, I want to at least maybe kind of draw what my mesh looks like. That will be helpful. Basically just drawing a box around each one of those nodes. Hopefully this looks, I don't like how I did that. Okay. There, that looks a little bit better. I'll work backwards. There we go. And that one needs to go like that. Okay. Looks a little bit better, right? We can kind of see like the size of each one of those elements. All right, so I am going to do an energy balance. Do an energy balance on node 2. All right, so let's go look at node 2, shall we? So if I look at that guy, well, I have convection or conduction coming from node 1. I have conduction coming from node 3. I have conduction coming from node 6. And then I also have conduction or convection coming up at the top. So I'm going to erase those arrows so I can see what I'm doing. But so we're going to work our way around. And I don't have any energy generation. So it's just going to be those 4 vectors coming in. So looking at Q by conduction from the left-hand side from node 1. So it is going to be negative K. Oh, and by the way, you'll notice that for this particular problem, the node spacing is the same. So instead of plugging in 0.01 for all of these, I'm just going to call this L, and that way my equation looks a little bit prettier. So for the node 2, it's going to be K, and from 1 to 2, it's a half area, so this is going to be L over 2 times the 1, and then I've got T2 minus T1, which I know, over L. All right, then I'll have one coming up from number 6. So I've got conduction from 6. So negative K. This is going to be going through that full area there. So don't need to have anything over 2. It's just going to be L times 1 into the page. And then I've got T2 minus T6 all over L. You can see those L's are going to go away. So maybe it doesn't matter that I, whether I know it or not, we'll see. Minus, and then I have one coming over from number 3. So it's going to be, and this is the one coming from over here is going through a half area. So negative K L over 2 times 1. And then this is T2 minus, oh, I don't remember. Maybe it was this one. Minus T3 over L. All right, and then I also have a term for the convection at the top, and that's coming through the full area. So this is going to be H times L times that 1 times, and this will be T infinity minus 2. Minus 2, sorry. Minus T2. There we go. And all of that is equal to 0. All right, so it looks terrible, but I mean, you can see already that those L's are going to cancel out for the first 3 terms, and so it'll look a little bit better, right? And so I have one equation and really just one unknown, so I do have a value for T1. So my T1 ends up being, or I'm sorry, T1, I know T1, I'm sorry, T2. My T2 ends up being 422 Kelvin. So I'm going to box that. Perfect. All right, so I got number 2. Now I need to go to number 4. So energy balance on number 4. Perfect. All right, so let's go look at 4, because if you notice, it's got like this diagonal, and that seems problematic. However, that line right there, this line, that's a line of symmetry. So line of symmetry, meaning that that's the line across which that temperature distribution is a mirror image of itself. So a little bit smaller, because I don't want to forget that, well, there is material out there. Just because I was looking at a certain chunk of it, there is material out there. And right, just kind of coloring him in, it's still material out there. And so if I kind of continued thinking about it, okay, well, that goes like that, goes like that. I think that's really all I need to do. If I think about what the temperature distribution is on the other side of that line of symmetry, Well, this temperature right here, T3, it would be the exact same temperature, and I think I'm gonna, just so it has to be obvious, it's gonna be the same temperature as right here. Same temperature. So that temperature would be the same thing as T3. Because again, it's the mirror image. I kind of brought it all the way down. Right, this temperature right here, I could do the same thing. Let me make sure I'd have it the same. If I had to define like a temperature right here, this would be the same as T2, right? It's the mirror image of one another. This temperature right here would be the same as T6 if I needed it. You can kind of see where we're going there. All right, so doing an energy balance on that node 4 now becomes, okay, I could sort of see what we got to do because I have convection all along the outside of this channel, right? So, oops, don't like that. Still got T infinity, right? Still got that going. So if I do an energy balance on node 4, I have conduction from node 3. I have conduction, from that node 3. And then I also have convection through that half and that half. And so it's that area through which you've got convection is actually not half. It's a full area, right? So hopefully you can see that. So I'm going to erase those arrows so I just kind of keep things clean. And now I'm going to do my energy balance on 4. All right, so I've got Q by conduction from 3 to 4. So negative, oops, too skinny. Negative K, like that. Negative K. There we go. Times the area, and it's going to be a half area. So L over 2 times 1 times T4 minus T3 over L. All right. And actually, I've got 2 of those, don't I? Because I've got one from here and one from here, but they're coming from a node that's at the same temperature. So I think what I'm going to do is just, I'll multiply this by 2. And then I have, yes, I've got a Q coming from here and Q coming from here by convection. And so they'll be going through a half area. Yes, each of those would be going through a half area. In fact, I'll draw it like that. So we have our H, and then it's a half area. So L over 2 times 1 times, get our T infinity minus T4. But again, you've got 2 of them going through that half area. So yeah. And I guess that's it. And all of that is equal to 0. Got one equation, one unknown. I end up having a T4, which is equal to 360. Oh, I can't read. 363. 363 Kelvin. Perfect. All right. So that's for 4. Now I need number 7. So that's this one right here. And that's an interior node. You can see now that I've sort of like extended. Could you please briefly explain half area versus full? Yes. All right, so I'm going to zoom in here. So the node that we just did, this distance, oh gosh, stop it. You go over here. This distance right here is L over 2. And when you're talking about the Q, well, the area, it's going into this element, but it's going through an area that's half L over 2 times 1. If, say, I wanted to look at, I wanted to see Q going like through there, well, this distance right here is L. Right, so that would be a full area, just L times 1. Does that make sense? Okay. Okay. So we are doing an energy balance on node 7. And before I kind of filled in that, oh yeah, well, this is, you know, the picture that was drawn was just a section, but I do know that there is other material there. And so taking advantage of that line of symmetry is useful, because now what I have is an interior node. And an energy balance on an interior node is super simple. We got one here, we got one here, we got one here, we got one here. Okay. And if you recall, let's actually go look. First equation that we wrote down, how easy this was. This was on an interior node. That's what we had. We had an energy balance on an interior node. And you could see that, boy, I mean, if you're going to memorize one of those equations, that's a good one to memorize, right? I mean, you should be able to derive it, but that's a good one. Easy one to derive. Clearly, we don't have any Q dot, so we wouldn't have any of that term. We just have those temperatures. So you can see it's the temperatures of the surrounding nodes, 1, 2, 3, 4, minus 4 times the temperature of the node of interest is equal to 0. So let's go back over here. We're looking at node 7. And the temperatures of the surrounding nodes, I've got 2 of them at T3 and 2 of them at T6, right? 2 of them at node or at temperature 3, and then 2 of them at temperature 6. So let's go add those guys up. So energy balance on node 7. All right, interior node. So I have 2 times T3 plus 2 times T6, because I have 2 of each of those, minus 4 times the node of interest, which is T7, and all of that is equal to 0. And so one equation, one unknown. So I get a temperature for node 7 of 443 Kelvin. Perfect. All right. Very last thing I need to do is figure out the heat loss per unit length of the channel. So let's see. Heat loss per unit length of the channel. All right, so what we're looking at is the heat loss to the surrounding convective environment. So what I'm going to do is I'm going to zoom in, and I'm going to define, okay, well, that's fine. So we have, stop it. We have this Q. We have this Q. We have this Q. We have this Q. And I realize, yes, I also have it on the other side, like going out to the right, right? However, what I'm going to do is I'm just going to remember that this little chunk that they originally drew is a, if I figured out the temperature distribution from that one little chunk, I figured it out for the rest of it. And then the flip side of that is also that if I figure out the heat transfer per unit length for that section, well, you can see that there are going to be 1, 2, 3, 4, 5, 6, 7, 8 other chunks that make up this entire thing, right? So if I figure out just the heat transfer per unit length for this and then multiply it by 8, I've got Q per unit length. Okay. So that's what I'm going to do. So for B, I'm going to calculate the Q per unit length, and we'll talk about that Q per unit length in a second, for the top surface of the not the element, but because each of those boxes is an element, so I don't want to, of the section. And then multiply by 8. Okay, perfect. Now if I did, by the way, that's the way that we're going. I could, since I sort of filled in the rest of that information, I could also say, well, let me figure out this and this and this, and well, I'd have to go around the others. You know what? Yeah, just leave it. So I'm gonna calculate it for that chunk right there and then multiply it by 8. That's what we're gonna do. Okay. All right. So Q for number, or if I can, hold on a minute. I just want to have this in my,
Why are we multiplying by 8 again?
because you've got 8 of those sections. Hold on a minute. There we go. You have 8 of those sections, right? So that like black squiggly, that's this guy. So you have see, you got 8 of them. So if I figure out if I figured out the Q coming from the top of this, and then just multiply that by 8, because there's 1, 2, well, that'd be 3, 4, 5, 6, 7, 8. You see? Erase all my ugliness. Hopefully that's okay. All right, so I'm going to figure it out. I've got 4 of these vectors that I've drawn up because it's asking me for the heat loss. So that's indicating that it's going out. And there you go. So for the first one, so I have, for number 1, all the way to the left, that's going through, that's convection through a half area. So this area right here would be L over 2 times 1. So that first one, Q per unit length. Oh, and it's Q per unit length, which is, well, per unit length, it's linked into the screen, right? Because this is just channel. We're looking at a cross section. So it's Q into the screen. That's this guy right here. And so it's Q H times area, but area divided by that 1. So I'm not even going to write the 1 anymore, but it is a half area. L over 2 times, and this will be T1 minus T infinity. Then I'll have another one. So I have the second node, so at T2. So this is going to be, and that's going through a full area, L times 1 times 1, but it's divided by 1 because it's per unit length. And this will be T2 minus T infinity plus, now I got T3. So this is H. This is another full area. So HL T3 minus T infinity. And then this last one is a half area. So plus H L over 2 times T4 minus T infinity. So let's see. So this ends up being, this value right here ends up being 156 watts per meter. But for the whole channel, this would be Q per unit length. It would be 8 times 156 watts per meter. So whatever. So 1248. That's watts per meter. And that would be our final answer there. So we have another one that's kind of similar to this. And then problem 5 is relatively quick and straightforward. All right, so if you have any questions, just yell or throw it in the chat. Okay.
That you have up there, is that just like the two-dimensional flux or something? Because it's over like 1 unit length rather than over Q over A, right?
You're yeah, because yeah. I mean, it doesn't really matter because if yeah, you're asking why it's over 1.
I was just asking if that's just like flux or something, like because you just label it as Q single prime.
No, because flux would be double prime and it would be watts per meter squared. So the heat transfer per unit length, that's just the notation that they use, but it's length into the screen.
Sure. Right,
yeah.
thank you.
Okay. Right. So we'll move on. All right. So we have another flow channel, and so everything is symmetric. Everything is symmetric. We have 2 lines of symmetry here. So we have 1 line of symmetry. I'm going to highlight it, I think. 1 line of symmetry right here, and 1 line of symmetry right here. So yeah, so you could think of the mirror image on the other side. So probably what it appears to me like is that we could sort of extend this up. Okay, and then you could maybe define it like that. So you could define like another node up here to be 3. Right, and this one is 1. Still, there's a adiabatic surface here. So you've got like the little dots there indicating that all the way to the left, that's an adiabatic surface and you don't have any heat transfer for that. All right, so before we do anything, let's kind of read our problem statement and see what's going on. So we have, number 1, we do have internal energy. Yeah, we have volumetric, we have a Q dot. So I will write that. So our Q dot is 1 million watts per meter cubed. And then we've got convection on the top and the bottom, on the inner surface and on the outer surface. So on the inner surface, that's the one at the top. Yep, inner surface is at the top, and that's 50. There we go. So this guy is 50 degrees Celsius. This guy is 500. And it's watts per meter squared Kelvin. And then on the bottom, this guy's 25 degrees Celsius, and then we've got a heat transfer coefficient of 250 watts per meter squared Kelvin. Perfect. And then we actually happen to be given some temperature nodes, temperatures at some of those nodes. So rather than put them all at different temperatures, I'm going to just say the temperatures that we know, I'm going to put them in pink. I'll kind of put a little dot so we know T2. I don't know, actually, maybe I'll make an attempt. So our T2 is going to be in pink. That's that guy. And T3, he's going to be in green. So that's right. If I want to take advantage of thermal symmetry when I do my energy balances, that's what I'm going to do. T5, make him kind of orangey. So that's this guy. T6 is going to be purple. Okay. And then T8. It'd be kind of a neon green. Or neon blue, sorry. And then neon, we'll do neon green for T10. There we go. Yeah. If nothing else, it looks beautiful and colorful. All right, so we need to find the temperatures at nodes 1, 4, 7, and 9. And then we need to do a similar thing that we did in the previous problem, calculate the heat transfer rate per unit length from the outer surface. Yeah, so surface A and surface B. All right, so for A, part A. So we're going to do an energy balance. And I do have internal energy, I do have internal volumetric heat generation, so I will have one of those terms. So, right, E dot in minus E dot out plus our E dot G equals E dot ST. If I'm assuming steady state, which I'm gonna, this guy goes away. And so I've just got the E dot N and the E dot G. So we're going to do an energy balance on each of those nodes of interest. So the first one is node 1. So let's do that. All right. And then I think I will also kind of draw my mesh so it's really obvious when I have a half area versus a whole area. Yeah, that kind of thing. So let's go do it. A little dotted line right halfway between each of those guys. Go. Okay. There we go. All right. So looking at node 1, you can see that kind of taking advantage of symmetry, I can see that yes, I'm going to have conduction coming from the top and the bottom, both going through a half area, so essentially a whole area. And then I've got a Q coming from node 2, and that's going through a full area, right? Full area. Half area, add them together, it's a whole area. Okay, so let's sum them up. I'm gonna start from the top, and I'll treat them individually. So coming from node 3 on the top to 1. So I have negative k times the area. Again, it's a half area, and what we've noticed is that delta x and delta y, 25 millimeters, we're just going to call it L for, keeping everything nice and neat. So this is going to be L divided by 2 times that unit vector 1, and then it's going to be T1 minus our T3, which again, we know, divided by the distance between them, which is L. Now I'm working my way around, so I'm going to 3 o'clock, right? So the one coming from node 2. So plus a negative k, and this is going through a full area here. So this is going to be L times unit vector 1 times, I have T1 minus T2 over L plus, right, now I've got the one coming from the bottom there, and he's going through another half area. So this is going to be negative k L over 2 times 1 times T1 minus T3. And I guess I really, I could have, over L, I could have just multiplied this guy by 2, but that's fine. We'll write it all out. So that's as, I don't have any more Q's going into node 1, but I do have my volumetric energy generation term. So, so I do need a plus Q dot, and then it's going to be the volume of that element. But this guy right here is just a half element. So the volume is going to be L squared divided by 2. Right. All right. L squared divided by 2. And of course, yes, there's a in the z direction as well. And then all of that is equal to 0. And while it looks yucky, not that bad, I know everything except T1, so I should be able to solve for T1. And T1 ends up being 122 degrees Celsius. So I'm going to box that. Perfect. All right, so I've got node 1. Now I'm going to node 4. Right, so let's look at node 4. So the first thing that I notice is that when I'm calculating that volumetric heat generation rate, I'm going to need to multiply it by a volume. Well, this is 3/4 of the volume of an entire element, so it would be 3/4 L squared times 1 in the z direction. All right, slightly annoying because it looks like I've got conduction from node 2, 5, 8, and 3, and then I've also got convection as well. So only slightly annoying, but it's okay. Is what it is. All right, so coming from 2, I have negative k. Area is a half area, L over 2 times the 1, times T4 minus my T2 over L. L is going to cancel out. Now I've got it coming from T5. So coming in from...
Why is that one a half area?
Because it's half area. See that? And then this, yeah, and this is going to be a half area too for 5. Yeah, I'm sorry, I'm reading the chat. So what's the reason that node 2 is a full area instead of node 1? 2. Yeah, I think Ian was trying to answer for you that this guy is going through a full area. Yeah, we're just trying to take advantage of symmetry, right? Because it's not like nothing is going on above that line of symmetry. There is something there. Yeah. All right, but back to node 4. So I have things coming from that direction right there. So I have negative K, and then times the area. This is going to be another half area, L over 2 times 1. And then it's going to be T4 minus T5 over L. Then I've got another one coming in here from 8. This is going through a full area here. So plus a negative K times L times 1 times T4 minus my T8. Hopefully you can see that. That's pretty, yeah, there we go. Make it a little bit better. Minus T8 over L. All right, and then I've got one coming through here, and that's going through another full area. See, full area. So let's get that. So I've got minus K times L times 1. There's that area. And then it's going to be T4 minus T3 over L. Okay. And I think that's it. 1, 2, 3, 4 conduction terms. But I also have convection on that area and that area. So since it's 2 half areas that convection is going through, it's going to be just a full area. So plus H times L times 1. And this is going to be T infinity on the inner surface, that 50 degrees, minus the node of interest, which is T4. Oh, and I almost forgot, we also have internal energy generation. So Q dot, and again, it's times that volume, which is a 3/4 volume. So that's going to be 3/4 L squared, yes, times 1, right? And all of that is equal to 0. Whew, that was difficult. And so now we could just solve for the unknown temperature, which is T4. So T4 ends up being 94.5. So it's...
Hey, just double checking here.
Yes.
On the script for the third term, you have plus, minus, minus.
Ah. Yeah, let's erase one of those. Yeah, thank you. All right, so we got node 4. Let's do it again. Node 7. Here we go. So node 7, where are you? You're all the way down at the bottom. So it looks like when I'm going to be calculating that that volumetric heat generation term, the volume is going to be 1/4 of a full size element volume. All right, this one's not terrible. I have conduction coming from node 3. I have conduction coming from node 8. And then I've got convection coming in from the bottom. So should just have those 3 terms and then a Q dot term. So it shouldn't be too bad. All right, so for node 7, starting at the top. So negative K, so coming in here, and it's going through a half area. So it is L over 2 times 1 times T7 minus T3 over L. Okay, now I've got this one coming in from 8. So this is going to be plus a negative K. And this one's going through, oh, another half area. So it's going to be L over 2 times 1. And it's going to be T7 minus, make that just like, no, it's fine, minus T8. Like I should make it like just, I don't know. Maybe that's better, maybe not. T8 over L. And then we've got convection right here. But again, that convection is going through a half area. So I have plus an H. So H, that one, yeah. H, and it's the outer one, times the area, which would be, again, it's a half area, so it's going to be L over 2 times 1 times our T infinity outer minus T7. Whew. And then we also have a volumetric energy heat generation term, so that's our Q dot. And then, of course, we're looking at a quarter of the volume of a full element. So this is going to be times L squared times the 1 over 4. And all of that is going to be equal to 0. And from that, we can get our T7. So our T7 ends up being 95.8 degrees Celsius, and I will box that guy. Okie dokie. The very last one, we need node 9. So let's go ahead and get that guy. All right, so node 9. And instead of scrolling up every like 3 seconds, see if I can't. Yeah, perfect. There we go. Just so I'm not scrolling up. There we go. Put it right there. Perfect. All right. So looking at node 9. All right, so that's this one down there. So if I look at it, it looks like I'm going to have Q by conduction from 5, 10, and 8. You can see from 5, that's going through a full area. From 10, it's going through a half area. From 8, it's going through a half area. And then I will also have Q by convection going through a full area. So with that being said, let's go ahead and just write our governing equation here. And then when I calculate that Q dot, it's going to be a half volume of the element. So, all right, so starting at 5. So I have negative K. Area is a full area. So L times the 1, T9 minus T5, okay, over L, plus, then I have 1 coming from 10. I kind of like really, really neon green one. So negative K, and this is a half area, L over 2 times 1. Then I have a T9 minus the T10. Also pretty awful. Over L. Then I've got Q by convection. So that's on the very bottom. So plus, and that's through a full area. So H times L times the 1 times our T9. Actually, I'm sorry, T infinity. T infinity, and this is the outer surface, minus T9. And then I have one more conduction term, and that's coming from number 8. So this is going to be negative K, and that's a half area, L over 2 times the 1 times T9 minus T8. Again, you probably can't see that, so I'm going to kind of trace over it a little bit, over L. And then you've got your volumetric heat generation And this is in a half element. So plus q dot times, so it's L squared times the 1, but divided by 2. And all of that's equal to 0. And so now I could just solve for T9. So I've got T9, he's equal to 79.67 degrees Celsius. And I will box that guy right there. Okay. So part B is asking us, part B is asking us to figure out the heat rate per unit length from the outer surface. So that's on the very bottom, surface A. So we want Q per unit length for surface A. Okay. Now, if I look at those lines of symmetry, remember I've got one here and I got one here. It looks like this is probably, you have 4 chunks of these, right? You have one mirror image up top, and then you also have mirror image this way, right? So kind of goes off like that, right? Like that. That's what it looks like. So when I calculate that Q per unit length for surface A, I'm going to interpret this that I'm going to calculate the heat transfer rate for this section. But then I also know that there's going to be a heat transfer rate for this section, and then also for the one up here and the one up here. And it's going to be, so once I calculate it for this surface right here, if I just multiply it by 4, I'll have it for the entire channel. Okay, so for this little section, Q per unit length, it's, well, per unit length, it's, I'm going to be dividing by 1 because that's the length into the paper. So Q per unit length, and again, so the way it asks, heat transfer rate from the outer surface. So I'll have a vector here, 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 and here. Right? I think I'm going to actually bring it down to the other line. So for this single surface, Q per unit length, Q with a single prime. So I'm going to look at the first node 7. It's a quarter of an area. So it's going to be, there we go. So it's going to be H, really like that. Going to be H for the outer surface times the half area, which is L over 2. But again, and then times the 1, but the 1's been divided out because it's per length, times, and this will be T7 minus T infinity out, right? And the reason that I haven't, you'll notice like up here it was T infinity first. Down here, T infinity is next. And the reason is the way that I've drawn those arrows, right? The reason, or the way that I've drawn those arrows up there, right? So it's going to be T7 right at the beginning of the arrow minus T infinity. Okay, plus, and then coming from 8, that's a full area. So it's going to be H for the outer times L times T8 minus T, minus this T infinity for the outer. And then coming from 9, again, that's a full area. So it's going to be H naught L times T9 minus T infinity for the outer, plus for 10, so this is going to be H naught times L divided by 2. It's a half area, L over 2 times my T10 minus our T infinity, the outer. All right. And that's got to be equal to something. So I end up getting, for this guy, I have 1117 watts per meter. So for the entire channel, remember you've really got 4 of those equivalent surfaces for the entire channel. So it would be Q per unit length would be 4 times 1117 watts per meter. So that would be, oh, I think I, so this would be 4 times 1117. So I have 4468. And that's watts per meter. All right. And then for part C, very similarly, right? You calculate it for this whole section right here, but you'd have 4 equivalent sections through which you're having heat transfer. So I'm going to calculate it for each of these. So I'm going to have a Q going this way. I have a Q leaving node 4, right? I'm going to draw like that. Leaving 5, leaving 6. So let's get those. All right. So for 2, and this time I'm only looking at this surface. So I'm not going to look at the flip side of that. So the area is just a half area. So this is going to be, I have for the little section, that Q per unit length would be, now I've got H inner, it's L over 2 because again it's a half area, times 1 but divided by 1 because it's per unit length, and then I've got this will be a T2 minus T infinity. Okay. And then I've got for node 4. Now node 4, it's going through this area and this area. So it's the equivalent of a full area. So this is going to be, this is going to be H times L times 1 divided by 1 times T4 minus our T infinity. Okay. Plus I've got one from node 5. It's a full area. So L. And then we've got T5 minus our T infinity. Then we have another one, and it's for the node 6. So it's going to be, again, got a H half area, L over 2, running out of room. So this will be T6 minus that T infinity. Yeah, I almost made it. Totally almost made it. And if I do the math, I would get that this Q for that little section would be 1383, and that's watts per meter. So for the entire section, we just multiply that by 4. So 1383 watts per meter times 4 see what that is. So 1383 times 4, I've got 5532. Okay. All right. One more. This one's relatively simple. And it's the last one. All right. So problem 5. We have, down, bring him over here. So we have two-dimensional heat transfer in a long solid body. There's no heat generation. We want to find the temperature of nodes 1 through 9. And then we've got the node spacing, L, is 2 centimeters. So it's the same in the X and the Y direction. Perfect. All right. So what I want you to note is that there are lines of symmetry here. And I'm going to draw them. I'm going to highlight them kind of in a kind of orangey. So you can see that there is a line of symmetry right here. How do you know? Well, you look at the temperatures, right? This temperature and this temperature are the same. This temperature and this temperature are the same. This temperature and this temperature are the same. This temperature and this temperature are the same, right? So you've got this mirror image. And then you have the exact same thing going on here. So let's see what this tells us. What that tells me is, looking at that first line of symmetry, tap it. Go away. So what that tells me, if I look at that line of symmetry, it looks like, well, this node and this node are going to be the same. So T2 and T6 are going to be the same. It looks like T9 and T1 are going to be the same, right? And then before we write that down, going back to 2, so 2 and 6 are the same. I also have a little line of thermal symmetry here, right? So let's just check that out. So it looks like this and this are the same, this and this are the same, this and this are the same, right? So you can see there definitely is one down the middle, or horizontally in the middle. There's also one right here. We see that because, okay, well, this and this are the same, 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 this and this are the same. Okay, great. So we have this lovely thermal symmetry here. So it looks like T2 and T6 are the same because of this line of symmetry. It looks like T2 is the same as T8 because of that line of symmetry. And what else? Same as T4 because of that line of symmetry. So T2, T6, T8, and T4. And then you can make a similar argument. In fact, I think I'm going to write those in red now. So let's calm down. There we go. Oh. Just so it's really obvious. So T2, T6, I'll write in order T4, T6, T8. So T4, T6, T8, 4. And then I could make a similar argument that, well, this guy and this guy, this guy and this guy, right? You can see that those are going to be equal to one another. So T1, T3, T7, T8, those are all the same. And we'll see about T5. I kind of think that probably that's probably going to be one that's going to be in red as well, but we'll see, right? We'll make the math tell us.
T7 and T8 are the same, or do you mean to say T9 at the end?
Oh, 9. Yes, I meant to say 9. Thank you. Perfect. Yeah, I have a feeling T5 is going to be a red dot, but let's just make sure. Yeah. So we're going to do an energy balance. So we'll do an energy balance on, doesn't really matter. Let's do it on node 1. And this is an internal node. There's no energy generation. So remember, it's that simple one that if you're going to memorize something, that's a good one to memorize. So it's going to be the sum of the temperatures surrounding. So I have 180 degrees plus 180 degrees plus a T2 plus a T4, which, oops, those are the same. Yep. And then minus the 4T1. Okay. So there's one equation right there in there. I want to kind of highlight this because that's one equation. In fact, I don't want to highlight it yet. Let's just rewrite that a little bit so that there's fewer terms. So this would be 360 plus 2 times T2 minus 4 T1 is equal to 0. There we go. I'll highlight that. That looks pretty. So that's one equation, 2 unknowns. All right. Now we're going to do an energy balance on node 2. Let's do node 2. All right, so that's that one right there. All right, so node 2, so I've got 200 degrees plus T3 plus T5 plus T4 plus T1 minus 4 T2 equal to 0, right? Do I have too many terms? 1, 2, 3. I feel like I have too many terms. I got a 200. I got a T3. I got a T5. I don't need a T4. I'm going to cross that out. T4 is diagonal. Up, 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 up. Cross that guy out. Yeah. Too many. And so I could rearrange this. Okay, well now this becomes 200 plus, and we'll write it as 2T1, right? We'll combine the T1 and T3 because those are equal to one another, plus our T5, which I have a feeling he's red, but we'll use the math to tell us, minus our 4 T2. And all of that's equal to 0. So that's one of them. And now we're going to do this, oops. Now we're going to do the same thing. We're going to do an energy balance on, let's do it on node 5. Okay. So for node 5, I've got 2, 6, 4, and 8. So T4 plus T6 plus T8 plus, there was a 2, 4, 6, 8. Okay. All right, T2 minus 4 times T5. Well, all that's telling me is that, all right, well, 4 T2 minus 4 T5 is equal to 0. So clearly T5 and T2 are the same. Okay. And so with that information, I'm going to plug that in there, maybe make that a little bit simpler. So now I've got 200 plus 2 T1 minus 3 T2 is equal to 0. All right, so I would combine this one and this one. 2 equations, 2 unknowns, and I could get what T1 is and T2. So I've got a T1 of 185 degrees Celsius, and then I get a T2 of 190. There we go. And that really just solves for everything because there was only 2 temperatures to worry about. All right, and so that is where we're going to stop tonight. Tomorrow we'll move on to transient heat transfer, and yeah, there you go. All right, thank you. I'll hang out for a little bit if you have questions. Yeah, Jacob, I saw your email. I'll email you, okay? Okay. So I am going to turn on my clock, but I'm still here. Okay.
I missed the number for one of these. Let me check which one it was. The Q per unit length for problem 3.
This one?
Problem 3.
Oh, 3.
The total one was 1248. Okay. 810.56. Okay, cool. Thank you.
Yep. All right. So I'm going to put the little timer on so it's not like I'm staring at you. But again, if there are questions, I'll back. All right. Thank you guys. Have a wonderful night.